This video segment 1B is devoted to a detailed description of activities 3 and 4. The third task in the sequence is one that the teacher will use a number of times over several days. In this task, the teacher specifies the configuration of the beads. The children's task is to show what the teacher specified and then to figure out how many people are on the bus, as shown by that configuration. Children are asked to try to do it without counting. See if you can use the colors of the beads to help you figure out how many people are on the bus. Before we discuss this example in detail, notice how this instructional activity is different from the previous one. In the previous activity, children were told the number of people on the bus, and their task was to show that using their racks in any way they chose. Here, children begin by moving the beads on the racks to show the configuration the teacher has, and they are then asked to figure out the number of people on the bus. The initial part of this task is interesting in and of itself. To make his rack look like the teacher's, the child has to essentially copy what the teacher has shown. How might he do that? What might he be thinking? How might that influence how he figured out how many people are on the bus? In this case, for example, a child might notice that all of the red beads have been moved to the left and also one white bead on the top. The child might move his beads in exactly that way, that is, move all of the red beads and move one white bead on the top. A child can do so without having any idea of how many beads he moved. To figure out how many people are on the bus, this child might have to then count the beads by one to get to 11. Another child might move the beads in the same way but might be thinking something entirely different. He or she might be thinking, I have to move all 5 red beads on the top and all 5 red beads on the bottom and also one white bead on the top. This child might figure out that 11 people are on the bus by reasoning, I know 5 and 5 make 10 and 1 more is 11. There are 11 people on the bus. Yet another child might move the 5 red beads on the top and 1 white bead on the top, and then the 5 red beads on the bottom. This child might then figure out how many people are on the bus by saying there are 6 on the top and then count on 7, 8, 9, 10, 11, while pointing to the beads one by one on the bottom. The class discussion that accompanies this task focuses on how the children figured out how many people are on the bus, and not on the order in which the child moved the beads. Of course, some children might talk about how they moved the beads as part of their explanation of how they figured it out. For example, the child that thought about the red beads as 5 might say, I moved 5 red beads on the top and 5 on the bottom. That's 10, and 1 white one is 11. When children explain that they figured out how many people are on the bus by counting by ones, it is useful for the teacher to ask, does anyone have a way to figure it out without counting? Or, can you use the colors of the beads to help you figure it out without counting? In this way, the teacher acknowledges that she is aware that some of the children still need to count, but that figuring it out without counting is more efficient and is a goal of this instructional sequence. After all, the teacher does have a mathematical agenda, and it is her responsibility to advance that agenda. One way to do so is to acknowledge when a child counted, but not devote time to having the child repeat that counting activity for the class. In addition to the example already discussed, consider these examples. In example 2, children that moved the red beads on each rod first and then moved the white beads on each rod might already have a concept of 5 as a composite unit. Some children might reason that 5 and 5 make 10 and then count on 11, 12, 13, 14 as they point to the white beads. Children that reason this way are often initially unaware that there are 7 on each deck of the bus. I want to make a comment here about the fact that I said such children might count on by ones from 10 to get to 14. Teachers that are new to using instruction of this type might be surprised by this. Wouldn't children just reason that 10 and 4 more are 14? The answer is no. Most first graders would not do that. In fact, most children at this point in grade 1 do not just know that 10 and a small number gives the relevant T number. That is, 10 and 3 are 13, 10 and 7 are 17, etc. Coming to just know this relationship between 10 and a small number is the corresponding teen number is one of the conceptual advances the majority of children make as this sequence progresses. Let's consider another example. In example 3, children might also use that approach. However, in this case, 1 or 2 children might use 10 as a reference point in the following way. A child might reason that there are 10 beads on each rod, and 1 on each rod has not been moved, so the number shown is 2 less than 10 plus 10, 2 less than 20. But what is that? The child will most likely figure out how many that is by counting back. 19, 18. I want to say something about these solutions that involve some counting on and counting back. Earlier, I said that a goal is that children use the color configurations of the beads to figure out how many there are without counting, explicitly without counting everything by ones. Many of the ways children reason on these tasks involve some counting. Why is that? It's because children do not yet just know the number combinations for small numbers, in particular for numbers between 10 and 20. Coming to know these is a goal of this sequence. It's a result of using these instructional activities. Therefore, the teacher has to be careful to not insist on no counting at all. Rather, the teacher's task is to continue to encourage children to use approaches that do not involve counting all by ones, while yet realizing that a few children will need to do so for some time. Here we show 2 examples of unproductive tasks. In other words, these are types of tasks not to use. Why do we call these unproductive? The reason is that there are no easy ways to capitalize on the color configurations to figure out the total. Even those children that see the group of 5 red beads on one rod will most likely have to count everything beyond the 5 by 1s to figure out how many in all. It is important that the teacher understand this point so that she can be deliberate in using only those tasks that are productive for advancing her agenda. Careful teacher planning is essential. Teachers that have used this instructional sequence successfully typically plan the tasks they will use in a lesson by thinking about how children will reason to figure out the total. In the instructional activity we have just been talking about, children figure out how many people are on the bus when the configuration is specified. The teacher specifies the configuration by showing her rack and telling students, "Make yours look like mine." There's another way the teacher can specify the configuration. Instead of showing her own rack, she can tell students how many people are on the upper deck and how many are on the lower deck of the bus. For example, the teacher says, there are 7 people on the upper deck of the bus and 8 people on the lower deck. Show that on your racks and then figure out how many people are on the bus. In this example, they have to think about how to show 7 on the top and 8 on the bottom, and only then think about the total number of people on the bus. Now, I want to be sure to clarify that this is not intended as an addition task. We do not expect that children will think, what's 7 plus 8? And it is important that the teacher not think of this as posing an addition task. At this point, children do not know what 7 plus 8 is. In fact, knowing sums such as this is the result of this entire sequence. That's the main purpose of part 2 of the sequence. Instead, this task asks children to use the color configuration of the beads to figure out the totality without necessarily thinking of it as 7 and 8 more. Posing the task in this way is simply an alternative way to ensure that all children have the same configuration on their racks. In other words, that they're all looking at the same thing as they try to figure out how many people are on the bus. You can see that one feature of posing the task in this way is that children have to figure out how to show numbers up to 10 because the number on each deck is necessarily 10 or less. So posing the task in this way has the potential to be particularly productive for those children that are still working on developing 5 and 10 reference relationships for numbers to 10. Remember that the patterning and partitioning sequence was designed specifically for numbers to 10. So we would expect that many children will already have well-developed concepts for these small numbers. A number of children will show 7 on the upper deck by moving the 5 red beads as a group and 2 white beads as a group. Once children have made the configuration on their racks and had time to figure out the total, the teacher conducts a class discussion in which children explain how they figured out the total. The ways they reason are similar to those we have already discussed for the earlier version of this task. As a pragmatic point, I want to clarify that even though the teacher did not show her own rack when posing this task, it is useful for her to do so as the discussion progresses so that she can use gestures to help elaborate and clarify the explanations the children give. Before leaving our discussion of this activity, I want to make one additional point. We have explained that an essential feature of this task is that every child's arithmetic rack looks exactly the same, and we have described 2 different ways the teacher can pose the task to ensure that children's racks are all alike. Most teachers we have worked with have chosen to pose the task in both of these ways, often intermingling them within a single lesson. In this way, they capitalize on the merits of both ways for the benefits of the students. All of the activities we have described so far are whole class teacher-led activities. Partner work provides a useful contrast. The activity we describe here is a partner version of the previous whole class activity. Here, children work with a partner to take turns posing tasks to each other in one of the 2 ways used in the previous whole class activity. Either one child uses his rack to show some configuration. The partner's task is to make his rack look exactly the same, to figure out how many are on the bus, and to explain how he figured it out. Or one child tells his partner how many people are on the upper deck of the bus and how many are on the lower deck of the bus, and the partner's task is to show that on his rack, to figure out how many people are on the bus, and to explain how he figured it out. The first time we tried this activity, we were unsure if it would be productive. We were concerned that children might show their partners some configurations that are not useful for learning. We were pleasantly surprised. For the most part, the configurations children created were reasonable. In addition, we were amazed at how many different tasks they posed to one another in a short amount of time. Whereas in the whole class activity, a considerable amount of time is devoted to discussing each task. In partner work, only one person is explaining, so much less time is involved in each task. As a point of clarification, when we explain the partner work, we tell students that the child that poses the task should know the answer to the task he poses. He should know how many people are on the bus. As a result, children typically choose configurations and make number choices that are appropriate for their current level of understanding. For example, the least sophisticated children often choose tasks such as 10 beads on the top, or all of the red beads, or 5 on one rod. The more sophisticated students, on the other hand, often choose more complex tasks, such as 7 on the top and 9 on the bottom, that require more reasoning and more explanation. It is essential that teachers understand an important principle that undergirds our approach to partner work. It is that each child is partnered with another child at a similar level of conceptual understanding. Partners should be close to each other conceptually. When students of very different conceptual understandings are partners, little learning takes place. In our approach, partner work is not a situation for tutoring. Our more sophisticated students need to be partnered with others that will challenge them, and our least sophisticated students need to work with others that don't tell them what to do. When will you use partner work? Teachers often like to follow whole class activities with partner work. For example, the whole class activity we have just described previously, followed by this partner activity, works well. Most teachers do not conduct a discussion following partner work. Those that do keep the discussion very brief, typically asking 1 or 2 students to describe something that happened in their group. What might children learn and do by engaging in the activities with the arithmetic rack that we have described so far? We have already said that children will do a variety of different things and reason in a variety of ways when moving the beads and figuring out how many people are on the bus. These ways are reflective of the children's current concepts of number. Of course, it is also the case that the ways children move the beads and reason change over time. These changes indicate learning. For example, a child that initially moves beads by ones and counts by ones to figure out how many people are on the bus will shift to moving groups of beads based on color configurations. In the process, such children develop 5 as a composite unit. Further, because of the support of the visual material provided by the rack, children also begin to organize quantitative visual materials in groups related to 5s, 10s, and doubles. And some will learn how the team numbers relate to 10, though many children will not develop that relationship until further in this sequence. At this stage, most children rely heavily on being able to use the rack and the support it provides because of the arrangement of the beads. But a further goal of the sequence is that children eventually become able to reason entirely mentally, that is, in the absence of the rack as a support. One step along the way is that they develop mental imagery for numbers to 20, imagery that is 5 referenced, 10 referenced, and doubles referenced. The next instructional activities in the sequence are designed for that purpose. Rack Flash is designed specifically to promote mental imagery. In this activity, the teacher flashes, not shows, some configuration on her arithmetic rack. The children's task is to figure out how many people are on the bus. And as in the previous activities, they are to try to do so without counting by ones. Now, during this activity, the children do not have their racks, so they have to rely on the images they see flashed on the screen. Let's give an example. The teacher flashes this image on the screen for 2 to 3 seconds, then removes the image and leaves it off for approximately 5 seconds. Then she flashes it again and removes the image again and repeats the process for up to 3 flashes. The flashing is followed by a class discussion in which children explain how they figured out how many people are on the bus. The discussion begins while the visual material is not visible. Typically, the teacher shows the image as the discussion progresses so that children can make sense of what they hear others say. As we have explained in earlier videos that describe flashing activities, the purpose of flashing is to promote mental imagery. In this case, imagery of the rack. How does that imagery develop? It develops because during the flashing activities, children have access to the visual material, in this case the rack, only briefly, but are nevertheless expected to solve the task posed. That means that they have to figure out how to use the image even when it's not visible. Some teachers say to the students, take a picture with the camera in your mind. What we know is that children organize the visual material mentally based on the ways of reasoning they developed when using the rack themselves in earlier activities. We know this because of the remarks they make in the subsequent class discussion when they explain how they figured out the number of people on the bus. For example, a child might say, first I saw all the red beads, and then the next time you flashed, I saw the 2 white beads on the top. Then the next time, I saw the 3 white beads on the bottom. The child might then go on to say, so I knew there were 10, and then I counted 11, 12, 13, 14, 15. Remarks such as these provide evidence that children's mental images are organized around 5s, 10s, and in some cases, doubles. As with all of the activities in this sequence, the discussion focuses on strategies that use groups of beads to figure out the total, with the full understanding that some counting, such as counting on, is often necessary. There is one additional important remark about this activity, and it relates to an underlying principle of our instructional approach. The principle is this: every child should have a personally meaningful way to participate in each task. That means that we have to accommodate the expansive conceptual development that is present in any classroom. We have to make it possible for the less sophisticated student to have a way to participate, while at the same time make it possible for the more sophisticated student to advance in his or her learning. We have described this task in terms of how it provides an opportunity for students to advance from using physical materials to using mental material as the basis for reasoning. However, in almost every class, there will be 1 or 2 students that still require the physical material to participate meaningfully. Therefore, we recommend that the teacher ensure that those students that need to have a rack have one to use. What will happen is that as the teacher repeatedly flashes the image on the screen, the children that have a rack to use will make their rack look like the image flashed and then use it to reason with. If more than 2 or 3 students require a rack, use of this activity is premature. In a partner version of Rack Flash, each pair of students has a rack, and they take turns posing tasks to each other as follows. One child creates a configuration on the rack and shows it to the partner. The partner's task is to figure out how many people are on the bus and explain how he figured it out. The difference between this partner activity and the one we described earlier is that here only the child that creates the task has a rack. The partner's task is to figure out how many people are on the bus without having his own rack to reason with. Of course, those children that still need a rack to use often touch the beads as they figure it out. We have found that it is not necessary that the child posing the task mimics Rack Flash to the extent that he actually shows and hides the rack repeatedly. It is sufficient that he shows the rack to the partner. Teachers often use this partner activity in the same lesson as the whole class Rack Flash activity. Many teachers find that following a whole class activity with partner work that is similar in nature provides a useful change of pace for the children while continuing to promote the intended learning goals of the lesson. This concludes video segment 1B. The next video segment 1C describes the remaining activities and a timeline.